In this video, we will continue our introduction to basic electronics with some multimeter procedures measuring voltage, resistance, continuity, and current. Brief introduction to an oscilloscope and electronic component review and some simple schematic drawings. And then we will talk briefly about impedance, distortion, headroom, clipping, noise, and signal-to-noise ratio. To begin with, we're going to look at the multimeter, and the multimeter is probably the most common piece of equipment that you will use in your audio career. It can be measured or used to measure voltage, resistance, current, and continuity within a circuit. So to start with, to measure voltage, you hook the two leads to the voltage inputs of the meter, and then you connect those leads across a source of voltage. In this case, they're connected to a battery, and the left side of the battery in this picture, which is at the bottom, is actually the positive terminal, and they have that hooked up to the black lead, and then the negative terminal is hooked up to the red lead. And red is typically your positive lead. So you're seeing a negative reading on the meter because it's technically connected backwards. But if you look at it, the leads are connected across the component that you're measuring the voltage of. Resistance is also measured across the component. So we hook the two test leads to both sides of the resistor, and that little tiny thing with the colored bands is a resistor. And remember, resistors resist electricity flow or electron flow. And in this case, we're seeing a reading of 0.97. So this is probably a 1 ohm resistor. And with a tolerance, it's slightly lower than 1 ohm. The next thing you can measure is continuity. And in this case, there's no picture to be shown. Basically, if you just put it in the continuity setting, as can be seen on the left side at about the 8:30, 9 o'clock mark, it's used primarily for testing diodes and just circuits to make sure that there is current flow. And it just makes a noise and then shows a 1 if there is continuity, and it shows a 0 if there is no continuity. The current sensing is actually one of the strangest measurements with the meter, and in this case you basically connect the meter in series with the thing that you're measuring the current, but you have to make sure you don't exceed the limits of the meter, because some meters can only handle 1 amp. Some meters can handle more than 1 amp. In this case, this meter can actually handle up to 10 amps, but you would need to move the red lead from the right-hand side to the left-hand hole marked as 10A for 10 amps. So you've got to be careful that you don't exceed the working limitations of the meter when you're testing current. But current is connected in series with a circuit, whereas the other measurements, the resistance and the voltage, are measured in parallel. The oscilloscope is a device that is used to measure the changes in voltage over time. And in this case, you're seeing in the meter or in the oscilloscope a AC signal that is being measured from the circuit in the lower left corner of the screen. This is the output that we normally look at when we look at audio, because we're looking at audio as voltage usually changes in voltage, and therefore we see it going above and below that center line, which is your 0 point. The next thing we're going to look at is a review of some of the electronic circuit components that we saw in a previous video, and we're going to see how they get put together and how they're drawn on paper to make complete circuits. So in the first circuit we're going to look at, it's simply a battery and a light bulb hooked up together. Now, if you remember our voltage equals current times resistance formula, we are given a voltage and we are given a resistance, so you can actually apply those calculations to figure out what the current is flowing through this particular circuit. I won't do that here, but I would encourage you, maybe try out the equation and solve for I and see if you can figure out how much current is flowing through this circuit with a 12-volt battery and a 100 ohm lamp or resistive element. Now we're going to add a switch to our circuit. So as you can see, the switch opens the circuit or closes the circuit. So now you can turn the lamp on and off. And now you basically have an old school simple flashlight. The third thing we're going to add to this circuit, or the next thing we'll add, is a resistor of 100 ohms. And it's the same resistance as the lamp. So now the circuit has a total of 200 ohms. The voltage remains the same, and you could again use that same equation to figure out what the current flow is when the switch is closed, and you'll find that the current flow is probably about 1/2 of what it was when you had the lamp alone. And since the resistor and the lamp are in series, if you remember from our resistor measurements, you're simply going to add the two together. So the total circuit resistance here is 200 ohms. And since the current flow is half, the lamp will be dimmer than it was without the resistor. This is one kind of a schematic that shows the actual flow through the circuit. This is typically called a schematic. And the next things we're going to look at for the microphone, amplifier, and speaker are also schematics, but they are more of a block diagram schematic. So in this case, we see the microphone on the left, the amplifier in the middle, and the speaker on the right. When you speak into the microphone or play music into the microphone, it's going to come out the speaker either louder or softer than it started, depending on the level of the amplifier itself. If we want to add a switch to this circuit, we could turn the microphone off with the switch, and then we can also add a variable resistor to the input of the amplifier, and by changing the resistance, you're going to change the current flow from the microphone to the amp, therefore changing the volume of the output. These are basic diagrams just to kind of give you an idea of what you might be looking at in future classes in the program. The next thing we're going to talk about is impedance. And I kind of mentioned this a couple lectures back. I said impedance is the AC equivalent of resistance to a DC circuit. The thing that makes impedance different is that it's dependent on the frequency of the signal. Usually we're talking about AC signals for audio versus DC signals. So the impedance is a measure of the opposition that a circuit presents to a current when a voltage is applied. So basically, it's the AC resistance of the circuit. In addition to the resistance as seen in DC circuits, impedance in AC circuits includes the effects of the induction of voltages in the conductors by the magnetic fields and the electrostatic storage of a charge induced by voltages between the conductors within the circuit. The impedance caused by these two effects is collectively referred to as the reactance and forms the imaginary part of the complex impedance calculations, whereas resistance forms the real part. So for all intents and purposes, in most of our discussions, we will say the word impedance, but we will think of it as the resistance. And by the way, the imaginary and the real part that we're talking about there has to do with calculus, and that's way beyond the limits of this class. When two pieces of equipment are connected together, their impedances should match or be roughly equal. In other words, if you have a 600 ohm microphone, you want the input of the amplifier to be roughly close to 600, or preferably the output impedance should be lower than the input impedance. So if the microphone's impedance is 600, that's the output. it should go into a slightly higher input impedance on the amplifier if they cannot be matched. If the impedance between two pieces of equipment is too great, they will cause the signal to degrade in three different ways. Either a voltage loss due to the resistance, a change in the frequency content due to the capacitance and the inductance, that's the impedance change of the signal, and reflection, which is where the impedance and the resistance to the current flow is so great that it's easier for the signal to bounce back to the source instead of going into the next leg of the circuit. Loudspeakers are measured with impedance as well, and the impedance measurement is also the ohm. So if you were to take an ohm meter, which is that multimeter we saw earlier in this video, if you were to connect the ohm meter across the speaker terminal leads, you would be measuring the DC current through the speaker, and it would be roughly 20% lower than its AC impedance. So the DC resistance of an 8 ohm speaker is going to measure somewhere around 6 ohms. A 16 ohm speaker will measure around 12 ohms of resistance. And it's generally not advised to mix different impedances in the same circuit because the speaker with the lowest impedance, the least resistance, will do most of the work. The equations for calculating impedance are the same as those for calculating series resistance, as you can see on the left picture, and parallel resistance on the right. So those are the same equations, but we've just substituted the letter Z, which stands for impedance, instead of the letter R, which stands for resistance. The next thing we'll talk about is distortion. And distortion is any change introduced by a circuit to the input signal, such as gain or attenuation, making something louder or softer, tonal changes, which is changing the frequency or the tone controls, noise, power supply ripple, which is a different form of noise, or any other interference. Any of these changes to the original input signal are called distortion. Some of them are desired, such as the gain or the attenuation or the tonal changes if we're using an equalizer to change the frequency. Some are not desired, such as noise or the hum of a power supply or other interference from lights or anything else in the area. And distortion is measured by subtracting the output signal of the unit being tested with the phase-inverted original input signal. And under perfect conditions, the phase change of the input added to the output would result in zero, a 0-volt signal, meaning that there is no distortion at all. Unfortunately, in practice, this never occurs. There's always some residual leftover signal that's greater than the 0 volts, which is the raw distortion that's being preserved. And we measure distortion as a percentage of the full input signal amplitude. Now, a type of distortion is called harmonic distortion. And if you remember, we talked about harmonic overtones earlier in the course. Harmonic distortion also follows the harmonic sequence 2 times, 3 times, 4 times the original frequency being added by the circuitry that the signal is passing through. Second harmonic distortion, many audio engineers call this good distortion because it's 1 octave higher than the original signal. And therefore it actually sounds very similar to the original signal, and therefore it doesn't conflict with it. And a special effect unit that intentionally adds second harmonic distortion is called an enhancer, and you can control the amount of the second harmonic that is being added to the original signal. By adding the second harmonic, the overall sound sounds brighter, and the effect is unable to be accomplished with tone or EQ adjustments because you're actually adding an additional component that wasn't in the original sound. The other type of harmonic distortion is called total harmonic distortion, or THD, and you will sometimes see this listed in the specifications for pieces of audio equipment, audio gear. And this is the measurement of the total harmonic distortion present in a signal, and it's defined as the ratio of the sum of the powers of all of the harmonic components to the power of the fundamental frequency. So if you look at the pictures below, the signal on the picture on the left, you can see the gray input sine wave and the red ripply output. All of those little peaks and valleys that deviate from the original gray signal are distortion, and those would be added together, and then the total of all of those either added or subtracted values, positive or negative values, would be the total harmonic distortion. The picture on the right shows that pure sine wave, and then on the right-hand picture, you see how that sine wave is distorted with third and fifth harmonics added to the signal. THD is the sum of all of these distortion factors that have been added to the original signal, and the lower the THD, the better. Crossover distortion is a type of distortion that's added to an amplifier where the components within the amplifier, in this case push-pull transistors, are not correctly balanced. And if you look at the right-hand side of the left-hand picture, you can see that little center point where the one transistor, Q1, handles the top half of the wave and Q2 handles the bottom half, but their timing is not correct. So you're adding a little bit of distortion with that flat line at 0 as one transistor shuts off and the second one turns on. These are audible differences, and they will create a harshness to the sound. So amplifier designers go through great extremes to make sure that the transistors are properly matched and so on. Looking at the two wave diagrams on the right, the left one is showing a perfect sine wave output, the purple wave, and on the right you can see what happens when that crossover distortion is present. It changes the shape of the wave, which will be audibly different. The next type of distortion we're going to look at is intermodulation distortion. And this is similar to crossover distortion in that when two signals with different frequencies are combined, a perfect amplifier would produce a mixed output signal that includes the two signals at their exact same frequencies and the same balance of their levels as presented at the input, nothing added and nothing subtracted. Realistically, though, every amplifier has some degree of nonlinearity, and it will produce additional frequencies that were not present in the original signal. And these additional frequencies are differential harmonics, which we talked about earlier, and they are added to the original signal, and they are called intermodulation distortion. So that is the section on distortion that we'll talk about. The next thing we're going to talk about is headroom. And headroom refers to the amount by which the signal handling capabilities of an audio system exceed the designated nominal level. In other words, your audio equipment is set to run at a nominal level, and it's usually on the audio meter, you would see it as 0 dB, or you can consider that maybe if you look at the volume knob on your amplifier, your stereo, a pair of powered speakers, maybe the number 8 value is considered the nominal level. Headroom is the level above that, which acts like a safety zone, allowing transient sounds, loud sounds, for example, a drum or somebody screaming, to exceed that nominal level without damaging the system or distorting the audio signal. And that distortion we will talk about next. It's called clipping. But anyway, so headroom in an analog piece of equipment is determined by the DC power supply voltage. If the AC headroom of a professional live or line level equipment is generally 1/3 of the available DC power, so if the power supply is 18 volts, the total peak to peak voltage, since it's AC going above and below the 0 point, is 36 volts. The headroom would be roughly 1/3 of that, or plus minus 12 volts. In the dBu world, if you convert it to dBu, it would be plus 24 dBu. Nominal professional line level equipment runs at about 1.23 volts RMS, and we will not talk about RMS in this lecture. And that is equivalent to plus 4 dBu, and therefore a maximum undistorted output is plus 24 dBu. The available headroom is 20 dB. Now, we talked a moment ago about clipping. Clipping is what happens when the output signal exceeds the range of the power supply. So if you look here at the bottom left, you see the input signal prior to being amplified is a pure sine wave. And then after amplification, if the amplification is too high, the signal cannot exceed the positive or negative power supply voltages for the equipment. Therefore, you get that flat top and flat bottom to the wave, where the original wave would have extended to the dotted line, rounding out the bottom and the top. This distortion is converting basically the sine wave into a square wave. And if we remember from the earlier lecture, the sine wave had a nice soft sound, but the square wave was very harsh. And this is typically what happens if you turn your guitar amp up too high and you start clipping, you start getting a real harsh output signal. Sometimes this is intentional if you're using a distortion or an overdrive effect. But if it's not intentional, it is a type of distortion called clipping. Asymmetrical clipping will also occur. Asymmetrical means non-symmetrical. Will occur in equipment that has a bipolar power supply, meaning a positive and a negative voltage power supply, if one half of that power supply fails. And in this case, you can see the input signal is the red sine wave. And since part of the power supply has failed, the negative part, all you have in the output is the green signal, and it drops down to the 0 point but fails to go below 0 and complete the other half of the wave. And again, this is going to sound very harsh and distorted because that flat line at the bottom is adding a whole bunch of odd harmonics to the signal as it clips. The last thing we'll talk about in terms of the generic distortion is noise. And when noise is added in an electronic circuit, it is basically usually kind of like a hissing sound, and it is caused by the random fluctuation of the current flow caused by the actual movement of the electrons jumping from atom to atom. And as that's amplified, it becomes audible. And it is an unavoidable characteristic in all electronic circuits. Using special materials for critical applications, the noise can be greatly reduced, but it's the hiss that you hear when you turn the amplifier up and there's no input. That is the noise being generated by the circuit itself. And the noise is measured as a signal-to-noise ratio, SNR, and it is a measure which compares the desired signal level to the level of the background noise, and it's expressed as a ratio. And you can see the equation is our 10 log equation, with the signal level on top and the noise level on the bottom. And it can also be expressed as a subtraction problem, taking the 10 log of the signal and subtracting the 10 log of the noise. And that is signal to noise. All electronic circuits at a temperature greater than 0 Kelvin, which is extremely cold, will cause some amount of noise, because at 0 degrees Kelvin, all molecular motion ceases. So basically, there won't be any electric circuit. Noise is generated in electronic devices for or by many reasons. One of them is the operating temperature of the circuit. The hotter, the more noise. So keeping your audio gear as cold as possible is definitely helpful, which is sometimes unavoidable here in Florida, where outdoor concerts tend to have the amplifiers sitting in the sun. The conductive and especially the resistive materials used in a circuit also tend to add noise. And then the amount of amplification or gain applied by the circuit to the signal will add noise as well. Dirty connections or dirty switches or dirty volume controls will also add noise. And then bad solder joints, which are the little tiny silver blobs that hold the components to circuit boards, when disturbed, cold, overheated, or corroded, will also cause noise. And then corroded or rusted or contaminated wires or circuit boards, and the contamination will usually come in from moisture in the wires or the circuit boards, will also cause noise.